So this presentation today is presented by the First Nations Adult Education School Council with the financial participation from Indigenous Services Canada. And we have Andre and I believe Natalie that are going to be joining us here a little bit later today. So a big thank you to both of you for the financing to give this course here. The course outline, we want to have you understand where radon comes from and its characteristics. Understand the health risks associated with radon, because there are specific health risks when we talk about radon. Understand how soil gases, which includes radon, infiltrates into the interior of buildings. Implement methods during the construction that will reduce the infiltration of soil gases, which includes radon, and understand the requirements relating to radon in the national and provincial building codes. And again, here we're going to refer to the National Building Code, the 2015 version, and the Quebec Construction Code 2015 version. So we're going to start off by talking about the health effects from radon and radon decay products. Where does radon come from? Essentially, it comes from the ground. And it comes from the natural decay of uranium and radium in the ground. And we find radon everywhere in the world. There's no place in the world that we could say has zero radon. Even outdoors, if I was to take my radon meters outdoors, I'd be measuring radon outside. So it comes from the uranium and radium that is found in the Earth's crust, and it's found everywhere. It typically moves up from the ground to the air above. When it comes out of the ground outside, it gets quickly diluted in the air. So typically for measuring radon outside, the levels would be very, very low. When it infiltrates inside of a home, nowadays we have the tendency of building our homes very, very airtight. So when radon infiltrates into that kind of a home that's built very airtight, it just stagnates there for long periods of time and will build up in certain cases to levels that are dangerous for our health. So we're going to see how that infiltrates into homes and what we can do essentially to try to minimize that infiltration into the homes. One of the things that we're noticing nowadays that probably the most polluted air that we're breathing is inside our own homes. The homes that are built so airtight that there's essentially no more fresh air that infiltrates, around windows, underneath doors, behind, electrical plugs and stuff like that. There's very little air that infiltrates naturally into our homes. If we went back, 30, 40 years ago, the quality of our windows, as an example, were not that great. So there was a lot of air infiltration from outside coming in through those windows. So if we compare the situation back in the 70s, maybe 80s, compared to nowadays, back then, you could easily be sitting in your living room watching television. And if you were sitting close to a window, as an example, in certain cases, you could actually feel and see the curtains move because of the infiltration of air that was coming in naturally around the window. We don't see that nowadays because the quality of the windows have really increased a lot, and our homes are getting really, really airtight. So that fact now is that, when we're cooking and we're doing different activities in the home, a lot of times that's staying inside the home. So we have odors sometimes that linger for very, very long periods of time in our home because the homes are so airtight. And that's why nowadays the national building codes or the building codes obligate us to mechanically bring fresh air into the home. And usually we do this with air exchangers. So if we didn't have an air exchanger, then we're not getting that fresh air coming in. But with the air exchanger, there's a constant flow of fresh air that's brought into the building at that point. And at the same time, there's a certain amount of stale air from inside that's essentially thrown outside. So nowadays, because the buildings are so airtight, there's that requirement for new homes, new constructions. Now, what is radon exactly? What are the characteristics of radon? So essentially, radon is a gas. It's not detected by human senses. In other words, we can't see it, we can't taste it, we can't smell it. It's naturally occurring. And we say it's naturally occurring, we could say that about outdoors. When it comes out of the ground, it gets diluted in the air outside, and it's not a problem for us. When it infiltrates into the homes, that's where it's a problem, because it could accumulate to levels that are dangerous for our health, as we'll see a little bit later. It's also radioactive. Now, anytime we use the word radioactive, what that simply means is that spontaneously, the atom, in this case here, radon, will disintegrate. And when it disintegrates, it's going to release energy, and it's going to change into something else. So in our case here, if we refer to radon, when it disintegrates, it releases a certain amount of energy, and it's that energy that's actually, that radiation we call, that's dangerous for us. And I'll explain that a little bit later, what I mean by that. But just remember, anytime we use the term radioactive, all it means is that for spontaneously, it's going to disintegrate, released, radiation or energy, and it's going to change to something else. It's inert. And what do we mean by that? Is that it doesn't mix with anything. You can't put anything into the air to remove it, kind of deal. So it doesn't want to mix with anything, doesn't react chemically to anything. It doesn't have a static charge. Now, when we're saying static, something has a static charge, it's like your shirt, your pants, your dress that has full of static. It has a tendency of sticking to different things, sticks to your legs, maybe your chair and stuff like that. So when we refer to, in this case here, has a static charge, if you did have a static charge, then it would have a tendency of sticking to stuff, sticking to the wall, sticking to the ceiling, sticking to the floor, to your clothes, etc. But because radon doesn't have a static charge, it just floats around. And there's nothing we can do about it. We say nothing we can do about it, but we can, if we can prevent it from getting into our homes, then that's a big step right there. So even though we say radon is naturally occurring, the way we build our homes, the way we design our homes, the way we use our homes, it's what's a problem here. And that's what actually, in certain cases, that's what actually causes radon to infiltrate into our homes to high levels in certain cases. So it's just the way we design, use, and heat our homes that actually is the problem there. So again, I got here a definition of what radioactive mean. And essentially we say, the technical description, it's subatomic interaction, which consists essentially of one atom spontaneously changing into another atom, also referred to as the decay process. So on the left-hand side, the upper image we see is actually an atom of radon. We've all seen that before. It's like the sun with the planets, traveling around the sun. Well, it's kind of the same thing here. You have a core of the atom, and you have electrons that are kind of floating around that core. Now, in the case of radon, what happens is you get a portion of that core that gets ejected. It's a particle that gets ejected out of the core of the atom. We call that alpha decay or alpha radiation. And what it actually is, it's actually a particle that gets ejected out of the core of the atom. In order for us to say that an atom of some sort is called radon, it has to have 86 protons. And what's in the core of the atom is actually protons and neutrons. In order for us to say that an atom is radon, it has to have 86 protons. If it doesn't have 86 protons, then it's not radon, it's something else, it's another element. So when that particle gets ejected, and that particle is always composed of 2 protons and 2 neutrons. So when it gets ejected out of the core, what's left has no longer 86 because it's lost 2 in that alpha particle. So what's left is there's only 84 protons. So that's now called polonium. And polonium is a metal. Actually, we call it a heavy metal. So as soon as that disintegration occurs, then the radon atom changes to polonium, which is a metal. So we go from a gas that changes into a metal. Why is that important to know? Is because when we breathe in the radon and the polonium, which are also radioactive, those atoms stick inside of, because they're actual metals, they get stuck inside our lungs. And you'll see that when that particle gets ejected out of the polonium atom also, it's going to create damage inside of our lungs. And I'll explain that a little bit later of what kind of damage that's going to be. So just remember that radioactive, all it means is that it's going to spontaneously disintegrate and release energy. And that's what energy is dangerous for us. To actually visualize, actually, I'll give you an analogy here. To actually visualize what's happening, I'm going to take the example of popcorn. Now, what do we do with popcorn is we take a small kernel of corn, we stick it inside a pot that's got oil, we stick it in there and we heat up the oil on our stove. And at one point in time, that kernel of corn is going to pop, it's going to disintegrate. In the process, it's going to release energy and it's going to change to something different. So if we compare the original kernel of corn, which is a small, hard, piece of a vegetable, it changes into a popcorn. It doesn't have the same color. It doesn't have the same size. It doesn't taste the same. It has completely changed. And in the case of radon, that's exactly what happens. Radon is a gas and it completely changes into a metal. In the process of the popcorn here, it releases energy. And that energy is strong enough to throw the piece of popcorn out of the cooking pot. So again, here, when we're referring to radon, that energy is what's going to be dangerous for us. And I'll explain that there. So in the atomic world, we can pretty well say that that alpha particle that gets released out of the core of the atom, the radon atom, it's like a cannonball. It's big, it's heavy, it doesn't go very far, but when it hits something, it does a lot of damage. And that's why I say that alpha particle, that radiation, that alpha radiation, it's what's dangerous for us, because when we have it inside our lungs, that radon that's inside the lungs, and that occurs, that disintegration occurs, then that alpha particle is going to hit living cells and it's going to damage the cells that are inside our lungs. What I'm going to show you here, and I took off the sound off this video because it's a French video. But essentially, it's a cloud chamber that was built in the laboratories, Health Canada's laboratories in Montreal. And it's essentially an aquarium. And inside, we have dry ice and alcohol. And they injected radon into the aquarium. And you're going to see all kinds of things flying through the air. We say that you can't see radon, you can't smell radon, you can't taste radon. But here you're going to see the radiation that comes off of the radon atoms. And as you're looking at it, you're going to see that there's a white plume that occurs inside that aquarium. So I'm going to play it and I'm going to kind of explain what's happening there as we're going through it. Oh, sorry. Try to play it. Okay, go back here. Try it again. Okay, it doesn't want to play for us, so I'm going to see here if I can find a way to get it to play. Okay, just hang on a sec. Here. Ramelia, can you see the video on the screen at the moment?
Yes, I can.
Okay, so I'm going to play it then. So what you're seeing here is Isabelle Vizino, that's actually in the lab in Montreal, Health Canada lab. And we're going to show you what happens inside that aquarium. What you're actually seeing is the alpha particles that are flying through the air. And the white plume that you're seeing is pretty well the same thing as when you're actually looking up into the air and you see a plane flying overhead. Behind the plane, you see this white plume of condensation. Well, essentially, this is what you're seeing here. The alpha particle is running through the air, and what you're seeing is that white plume that's behind the alpha particle at that point. You can see that the alpha particle is not traveling very far, maybe 2-3 centimeters. And again, we compare that to a cannonball. So when you're when it's big, it's heavy, doesn't go far, but when it hits something, it creates a lot of damage. So what you're seeing here is actually occurring all around you right now, because you have radon. If you're in your office, in your home, there's radon. There's no place on Earth that we could say has zero radon. So you have some in your home presently. So again, when it gets into the lungs and you have these alpha particles that are hitting their living cells inside your lungs, there's the danger there that we damage the living cells, and those cells could essentially be the start of a cancer. So how radon infiltrates into your home, again, it's coming from any cracks, any openings, any holes that you may have in your foundation walls or your concrete floor at that point. And it could accumulate to high levels inside your home. Now, because it's everywhere, it doesn't mean that because you have radon in your home that your neighbor has radon in his home. For sure, there's a certain amount of radon, but it doesn't mean that if you had high radon, that automatically he has high radon. It doesn't work that way. So every home is different. So again, here, this is happening all around you right now. Now, in Canada, the unit of measure that we use to measure the radiation from radon, we use the unit of measure called becquerels per cubic meter. And here again in the video, to try to minimize, we try to seal out the radon. And as we're going through our discussions, we're going to see during a new construction, what can we do to try to seal out the radon from make sure it doesn't get into our home or minimize it getting into our home. So as I was mentioning, in Canada, we use the becquerels per cubic meter. That's how we measure for radon. 1 becquerel is equivalent to 1 disintegration per second. So if I say 1 becquerel per cubic meter, I mean there's one of those disintegrations that occur for a cubic meter of air. So a box that would essentially be 3 feet by 3 feet by 3 feet high. So one becquerel per cubic meter, that's what it means. In Canada, the actionable level set by Health Canada is 200 becquerels per cubic meter, which means that if I took a box that was 3 feet by 3 feet by 3 feet high, or 1 meter by 1 meter, we'd have 200 of those disintegrations per second. Now, I want to do a little calculation with you right now. Like I mentioned, every home in Canada has radon. There's none that we could say has zero radon. If you, in your home, you measured, and let's say that you're just under 200. People use the 200. If I'm under 200, I'm safe. If I'm over 200, I got to do something. So let's say you're at 180. And you're in your room, your office is, let's say, 12 feet by 12 feet by, with ceilings that are 8 feet high. And I'm going to round it off to get the metrics. I'm going to say 4 meters by 4 meters by 2.4 meters high. I'm going to measure, I'm going to multiply that together. 4 meters times 4 meters times 2.4 meters. That gives me 38.4 cubic meters of air in the room that you are now. That's typical size of an office, 12 by 12 by 8 feet high ceilings. So just typically, that would represent 38.4 cubic meters. I'm going to multiply that by, because we know that 200 becquerels per cubic meter, and we said that you're at 180. So I'm going to multiply this number by 180. So we have 6,912 becquerels or disintegrations that are occurring in your room where you are, in your office per second. Now, if I want to find out in a minute how much disintegrations are occurring in a minute, I'm going to multiply that number by 60. So the number I get here, okay, every minute, if your levels in your home you measured and you had 180, which is below 200, in terms of disintegration in that office, you would have 414,720 disintegrations all around you right now, every minute. I'm going to repeat this. 414,720 disintegrations of that radon, those alpha particles running through the air per minute. Your chances of breathing some in, you're definitely going to be breathing some in. So we know that the risk for radon is actually lung cancer. So I'm going to explain how that actually occurs, but right now, the message I want to get across is your chances of breathing in that radon and having this disintegration, those alpha particle release while it's in your lungs, it's going to happen. I can guarantee it. Okay, so we've seen that video. So you've seen, the alpha particles flying through the air, and it's those alpha particles, when they hit living cells inside our lungs, that are going to create damage. The penetrating power. Now, when we're talking radiation, a lot of times we're going to talk about 3 types of radiation. Alpha radiation, which is actually an alpha particle running through the air, beta radiation, and gamma radiation. So beta radiation is a very, very small particle, and it'll travel like it's like a gunshot there. So the alpha radiation will cross through a piece of paper, but will not cross through our skin. Our skin is actually a good protection against those alpha particles. The problem is that when we breathe it in, we don't have that protection inside of our lungs. So when the alpha particle hits those living cells inside of our lungs, it's going to create damage at that point. The beta particles, they'll actually go through our skin. And the gamma, well, that's pure energy. It'll go even through concrete at that point. But the alpha particles, just remember that our skin is a good protection. And when we're referring to the health risks related to alpha particles or alpha radiation, it's especially lung cancer, because we don't have that skin inside our lungs that's going to protect us. So to simplify things here, okay, now essentially one of those alpha particles are in our lungs, and we mentioned that radon changes to polonium, which is a metal, and that polonium is also radioactive. It will also release an alpha particle. So when the radon changes to polonium and we end up breathing that in too, Because it's a metal, it's actually going to go down to our lungs and stay stuck inside the mucus lining that we have inside of our lungs. The actual radon itself, we're going to breathe it in, breathe it out, breathe it in, breathe it out. For the disintegration to occur exactly when it's in our lungs, the actual risk of that is pretty small. But in terms of the what we call the radon decay products or the poloniums, when we breathe it in, it stays stuck to our lining. So when it's going to disintegrate, it's going, for sure, it's going to damage living cells inside of our lungs. Now, those alpha particles, when they hit living cells, there's essentially three things that can happen. One, it's going to actually kill the cell. And if it kills the cell, it's not the end of the world, because we constantly have cells that are human cells that are dying in our body, and new cells regenerate themselves to replace that cell that died. A good example of that is blood. Let's say we go see a Red Cross and we give blood. If our body wouldn't regenerate the red and white blood cells, we would probably give blood 3 times and we would be dead. So we know that doesn't happen. So we know that our body is going to regenerate new red and white blood cells to replace the cells that we lost at that point. And that goes for all other cells in our body. There's always cells that are dying and new cells that regenerate themselves to replace those cells that have died. So to have that alpha particle hit a living cell in our lungs and it kills it, not the end of the world. New cells are going to regenerate themselves to replace that cell that died. The other thing that could happen is that it hits the cell, in not such a critical spot. The cell can actually repair itself. Like our body, if we cut ourselves, our body's going to repair itself. So essentially, the living cell can essentially repair itself if it's not too damaged too much. The other thing that could happen is that the cell survives. And for simplicity here, I'm going to say the brain of the cell. Let's say it gets hit with that alpha particle in the brain. And what could happen is that the DNA of the cell could get damaged. And if the cell survives, then at that point, what's going to happen, and remember here that we when we were born, we received a certain amount of DNA from our mother and a certain amount of DNA from our father, which gives us who we are today. So, we may have brown hair, brown eyes, we got 2 arms, 10 fingers, 2 legs, 2 feet, etc. So that's what determines what we are today, is that DNA. When the DNA is damaged, and in the case here, if the cell was hit just in the wrong spot and the DNA got damaged and it survived, at that point, when it's going to regenerate itself to replace a dying cell or a cell that died, because the DNA has been damaged, then we could end up with a cell that has 4 eyes, 4 arms, and 1 leg kind of deal. Okay, we call that a mutated cell. And the definition of a cancer cell is a cell that has sustained a mutation. So just remember that. What is the definition of a cancer cell? It's a human cell that has sustained a mutation. Now that mutated cell may actually become stronger than the normal cells. And we can kind of compare that today with the coronavirus, where the virus has mutated, and the new variant of the mutated cell is actually now becoming more contagious, maybe more dangerous to our health, etc. So we've actually lived that in the last 2 years with the coronavirus that has mutated into stronger, more contagious variants at that point. So that cell that is now mutated is actually what we call a cancer cell. And when it starts to disintegrate, not disintegrate, but regenerate itself, that's where we start getting tumors and cancer cells developing in our lungs at that point. So that's actually where the link is between radon and lung cancer, is that those alpha particles actually will damage the cell. Now, if the cell survives, there's always that danger that if the DNA was damaged, that it becomes a cancer cell. a mutated cell at that point. So that's the link between radon and lung cancer. Now, we don't see other types of cancers because we have our skin that protects us against the alpha particles, but in our lungs, we don't have that protection. So here's a small device that we use to measure radon. Some of you may have seen this, but I'm just going to stop my presentation here and I'll show you one. So here what I got in my hand is actually a alpha track radon monitor. It's a little puck that we put inside the home for 3 months, and then we send it to the lab. I'm going to show you what's inside this. It's a very simple device. I'm going to take off the cover. And what we see inside is actually a little piece of plastic. This little piece of plastic here. That's all that's in the device here. There's a little piece of plastic like this. And what happens is when the alpha particle hits that plastic, like the radon will infiltrate into this device, the alpha particle will hit that plastic and it'll make a mark, a track. That's why we call them alpha tracks. It's little pits, little marks that are made from the alpha particles. The question we have to ask ourselves here, if the alpha particle can actually make a mark on a piece of plastic, imagine what it's doing inside of our lungs. So this is a very common device that we use to measure for radon. By the way, if some of you have questions and you raise your hand, I don't actually see the raised hand. So Ramilia is going to tell me at that point if somebody has raised their hand or not there. So again, like I was showing you, it's simply a little piece of plastic that's inside the device. Radon infiltrates into the device and will release the alpha particle, and it's going to hit that plastic and make a mark. That's why we call it track, alpha track. When you send it back to the lab, what will they do? They'll take out that piece of plastic, they'll put it under a microscope, and they'll actually count the marks, the tracks on that piece of plastic. And depending on the number of marks they see, they'll be able to tell what the radon levels were in that room where you measure. So we see in the middle here, the alpha tracks hitting the plastic and making a mark, a track. Now, in Canada, cigarette smoking is still the #1 cause of lung cancer in Canada, but radon is the #2 cause of lung cancer in Canada after tobacco, and that's for smokers. For non-smokers, radon is the #1 cause of lung cancer in Canada. So if you know somebody that has never smoked in their life and got lung cancer, it's a good chance that came from radon. Just remember that. Now, it's estimated that 16% of lung cancers in Canada can be related directly to radon. And that represents, in terms of numbers, probably around 3,200 lung cancer deaths per year in Canada. So how does radon enter your home now? And we've seen in the video, any cracks, any holes, any openings that you have in your either concrete floor or cracks in the walls, there's a potential for the radon to get into your home. Anytime that you have either the walls, basements, or a roof, as an example, that's touching the ground, there's potential for the radon to get into your home. Sometimes people ask me, I have a home, it's a slab on grade, there's no foundation. Could I have a radon problem? Anytime that you have either your floor, walls, or roof touching the ground, there's a potential to have radon in your home. If you have wells in your community, there's a possibility, because remember that radon comes from the ground. So if you have a well that you dug to go and get water in the ground, then there's a possibility that you may have radon coming in through your water supply also. Now, how does radon actually infiltrate into your home? What's the mechanism that causes the radon to infiltrate into your home? Well, we can kind of compare that to a hot air balloon. And what we do with a hot air balloon is we heat up the air that's inside the hot air balloon. The hot air, being lighter, less dense than the cold air, will go to the top of the hot air balloon. And that's actually what's going to create a buoyancy force, which is going to cause your hot air balloon to rise into the air. Now, when we heat our homes in the wintertime and all the windows and doors are closed, the same effect happens. All our mass of heated warm air slowly rises to our ceilings. And our ceilings are never perfectly sealed. There's always some small openings around lights, corners of walls, around windows. Electricians made holes to pass their wires. Plumbers made holes to pass their pipes, trap door, etc. So you can imagine this mass of heated warm air that's slowly rising to your ceiling, and it eventually will find an opening to escape outdoors, typically through your attic. Now, during the heating season, the movement of this mass of warm air that's rising to your ceiling, it's continuously in motion, rising to your ceiling. And what it actually does, it causes your house to become like a large vacuum cleaner, creating a suction in the lowest level of your home. We call that stack effect. And it's this stack effect that's going to create this suction in the lowest level of your home. And that's what this suction that's actually going to draw in the radon from underneath your home in the ground through any cracks, openings, holes that you may have in your concrete floor at that point. So one of the prime locations for the radon to get into your home is a crack that forms between the foundation wall and the edge of your concrete floor. And the reason for that is when they originally poured your concrete floor in the basement and it started to dry, there was shrinkage that occurred. So with that shrinkage, what happens is you end up having a crack between the wall and the edge of your concrete floor at that point. That crack, in the majority of cases, is only about maybe a 1/16 of an inch wide. But at a 1/16 of an inch wide, it means that every 16 inches, we have an equivalent open of 1 square inch. And when we measured the crack around the whole perimeter of the basement, that opening could actually represent the equivalent of a hole that's about 1 foot by 1 foot, where the radon can infiltrate into your home. A lot of times we don't see that crack because we have insulation on our foundation walls and finishing, gyp rock and stuff like that. So a lot of times that crack is hidden behind the insulation, but it's there. And that's one of the prime locations for the radon to get into your home. Now, if you have a basement bathroom in your home, underneath the bathtub or shower that you have in that bathroom, the plumber typically leaves a nice big hole underneath the bathtub or shower so that he can go and install the P-trap. That hole could be as big as 16 inches by 16 inches underneath your bathtub or your shower. Once he's done his work, once he's finished installing his P-trap, a lot of times that hole is not filled in. So that's another big hole where the radon can get into your basement at that point. If you have a sump pump pit in the basement and you don't have a sealed cover on it, then that's another place. It's another highway for the radon to get into your home. Even your teleposts that you use to support the main beam of your home, those are hollow and they go, they cross through the concrete floor. So at one point, the radon can actually be coming into the basement through the center of those posts, which are hollow. So we can see that there's a lot of places, even a crack in the floor is another location where the radon can get into your basement. And like I said, you have this suction caused by the stack effect that's drawing it into your basement. So what we're going to see, we know that that's how radon infiltrates into your home. So what we're going to see is, can we somehow, during the construction, do things that would minimize or prevent the radon from getting into your home? So that's what we're going to be seeing over the next couple of slides. Can we do something, because we know what's causing it to come in? Can we do something to kind of prevent that from happening? So again, here, like I mentioned, your house actually during the heating season, because we're heating our home, is actually becoming like a large vacuum cleaner. And that stack effect that we're referring to here that's creating that suction is actually the major driving force, which causes radon to infiltrate inside the building, especially in the lowest level of the building. To understand the principle of what we're trying to achieve here, when we talk about an active soil depressurization system, because we'll be referring to that over the next couple of slides, the basic principle of that kind of a system is air will always move from a high pressure to a low pressure. And it makes sense. So if we have two rooms with a door in between, the room that has the high pressure will push the air through the door to the low pressure side. So that's the basic principle of what we're trying to achieve here. So on the left here, we have what we've seen previously. We have a house with a bunch of cracks and stuff like that. And we have this stack effect, this vacuum cleaner effect inside the home that's creating a suction in the lowest level of the home. Now, whenever we use the term suction, whenever we use the term negative pressure, what we actually mean is that we're doing a comparison between two zones, and the side that has the lower pressure is the side that we have a suction, or it's the side that's got negative pressure. So whenever we use those terms, because pressure can't be negative per se. So if we're using those terms, suction or negative pressure, we're always doing a comparison between two zones, and it's the zone with the lower pressure that we call the suction side, or we call the side that's got negative pressure. So in this home, we say that it's creating a suction in the lowest level of the home, but what we actually mean is that the stack effect is lowering the pressure in the basement. And at that point, if it's lowering the pressure in the basement, the pressure in the soil underneath the house is actually going to be higher now. So it's going to push the radon into your home through any cracks, any openings. So what we want to accomplish is try to do just the opposite. We want to lower the pressure underneath the concrete floor or underneath the house, so it's less than what it is inside the basement. And at that point, the pressure in the basement is going to prevent the radon from getting into your home. So on the right-hand side, we see here a active soil depressurization system where we're actually creating a suction underneath the concrete floor of the house. And we say suction, but what we're really referring to here is that we're going to lower the pressure underneath the concrete floor slab. So at that point, the pressure in the basement is actually going to become higher, and it's going to prevent the radon from getting in. So that's what we're trying to accomplish here. We want to reverse or inverse the relationship between what the pressure is in the basement versus the pressure below the concrete floor slab. Now, naturally is what we see on the left, because we heat the home. So essentially that's occurring naturally. The one on the right is we have to install piping, and in certain cases a fan, to create that lower pressure that we're seeing on the right-hand side. So again, it's like a tug of war. If we can create a suction underneath your concrete floor that's stronger than the suction that you have inside with that stack effect, the side that has the stronger suction will win the battle. It's like a tug of war. So that's what we want to kind of accomplish here with an active soil depressurization system. Now, when we're building new homes, we know what causes radon to infiltrate into the homes. So we ask ourselves, what can a builder do to reduce the radon risk? And we know there's certain, the risk is lung cancer in relation to radon. So what can builders do to reduce that risk? Well, we can implement methods during the construction which will reduce soil gas ingress. And in so doing, if we're reducing radon, we're going to essentially save lives, because there's a lot of lives that are lost because of deaths related to lung cancer. We're going to be talking over the next couple of slides of what's in the codes, what's in the building codes. And here we're going to refer to the 2015 National Building Code. So what are the main objectives of the radon-related changes in the 2015 National Building Code? Well, essentially the two objectives that, and for all the articles that we see in the building codes relating to radon, the two main objectives essentially minimize radon ingress into the building, try to prevent it from getting into the building. And if we can't, make it easy and cost effective to fix. So if we're able to find an easy way and a cheap way to fix it, that is the goal of what the articles are saying in the National Building Code. So those are the two objectives. So for the next couple of slides, I'm going to actually be giving you the article numbers in the codes and what they're referring to. So again, section 915, we're talking about dam proofing, waterproofing, and soil gas control. So again, that section there will relate to trying to minimize radon getting into your home at that point. So article 913.111, this section presents measures to control the ingress of water, moisture, and soil gases. And 4 applies to walls, roofs, and floor that are in contact with the ground. So like I mentioned, anytime that you have a portion of the house that touches the ground, whether it be the floor, the foundation walls, or in certain cases, we may even have roofs that may touch dirt, there's the potential for radon to get in to the building. Soil gas control, again, providing for the roughing for a subfloor depressurization system. And like the pictures we were showing, that's exactly what we're referring to when we say subfloor depressurization system. So we're going to provide for the roughing. We're going to put in the piping for that kind of a system during the construction. So we can go and get the radon underneath the concrete floor slab and hopefully not allow it to get into the building. Floors on ground shall be provided with a rough-in for subfloor depressurization consisting of a gas permeable layer, an inlet, and an outlet, as described in sentence 2. So again, here, what we're actually referring to is clean crushed stone underneath your concrete floor slab. Now, if you have clean crushed stone underneath your concrete floor slab, there's a lot of void space between the actual, pieces of crushed stone. So it's easy to create an air movement in between those stones there, the crushed stone. So the first step is having good, clean crushed stone underneath your concrete floor slab. Yeah, that's what we call a gas permeable layer. We have to have a pipe which is going to suck that radon from underneath your concrete floor. So we need an opening, a pipe with an opening in that layer of crushed stone. And we need an outlet that comes out of the concrete floor, essentially maybe a foot above the concrete floor. That's going to be capped off. So if we need to have additional radon reduction equipment installed later on, what we do is we simply cut that cap off the pipe and we take off from there at that point to install our what we call active soil depressurization system. When we say clean crushed stone, what we mean is that it's crushed stone and it doesn't have any fine particles mixed in with the crushed stone. In other words, no sand mixed in with the crushed stone. It's got to be clean crushed stone. I see a lot of times that a lot of contractors don't understand what clean crushed stone is. They'll when they're picking up the the crushed stone in a quarry, someplace, a sand pit or something like that. They're actually with the loader, they're actually picking up a lot of sand underneath the pile of crushed stone, and that fine sand is mixing in with the crushed stone. So we call that contaminated because there's a lot of that sand that's getting mixed in with the crushed stone. And what happens, that finer sand goes in and fills in the voids that are between the actual stones themselves. So it becomes more difficult to actually create an air movement through the crushed stone that has a lot of fine particles in it. So again, that's one thing a lot of contractors don't understand. It's got to be clean crushed stone. 913.4.3, providing for the rough-in of a subfloor depressurization system. The rough-in referred to in clause 1A shall include a gas permeable layer, which is that crushed stone, installed in the space between the air barrier and the ground to allow for the depressurization of the space. So what we're referring to here is that vapor barrier that you're actually installing on top of the crushed stone. So you want to depressurize the space between that vapor barrier that you have on the crushed stone or on the floor. and the actual ground itself. So essentially you want to create a suction only where there's crushed stone. An inlet that allows for the effective depressurization of the gas permeable layer, and an outlet in the conditioned space. So we're going to have a pipe underneath or running through that crushed stone that you have underneath your concrete floor slab. And essentially we want to run that pipe to the center of the floor. And we're going to see what the code gives us as options for doing that. So we want to be able to use the end of that pipe to go and suck the radon underneath the concrete floor through that crushed stone. And we want a small section of pipe coming through the concrete floor, maybe above 12 inches above the concrete floor, and it's capped off. And like I said, if we need it down the road, we simply cut off that cap and we take off from there. The air barrier or the vapor barrier that we see a lot of times, that has to be very, very well sealed. If it is not well sealed, then any openings, cracks, tears that you have in it, the radon is coming through. Now, the air barrier or the vapor barrier that we use a lot of times, the 6 mil vapor barrier, is very good at preventing radon from coming through. It's a good air barrier, good, radon barrier. But if we leave a lot of holes, tears in it, we don't seal it properly, then the radon is simply coming through at that point and getting into the basement. So any pipes that we're having that come through, if we have any plumbing pipes or even that small pipe that we're referring to here, the radon stub, when we actually have our going through our vapor barrier or our air barrier, we got to make sure that it's well sealed between the air barrier or vapor barrier and that pipe. Like, we just don't make a hole and that's it. It's got to be sealed. Otherwise, the radon will get through at that location. That small pipe that's sticking up above the floor, we got to make sure that it's labeled that only for radon. We don't want a plumber coming in down, 5-10 years down the road, say, okay, I have to put in a bathroom in the basement. I have a nice big 4-inch pipe here that I could use to tie in my toilet. I'm going to tell you, excuse the expression, but I think we're up the creek without a paddle here. So you don't want that happening. So we need to label it properly so that it's only used for radon. Again, I'm referring here, clean granular material, and the pipe has to be 4-inch. The pipe that comes through the concrete floor has to be minimum 4-inch or 100 millimeters. The bottom end has to open up into that granular layer because that's where we want to suck the radon from. So it's got to somehow have the open end inside that layer. If you sit it just on top of the vapor barrier, you're never going to be able to suck the radon through that crushed stone. So it's got to go into the layer of crushed stone. And that's where we want to suck the radon from. So again, as soon as we make a hole through that vapor barrier or air barrier, we got to make sure that it's well sealed between the vapor barrier and our pipe. We got to take those precautions to seal it properly. And we want our main suction to come from the center of the floor. Now, why is that? It's because if, as an example, we had a house that was 30 feet by 40 feet long, and we put our pipe, in one corner of the basement, and that's where our main suction is going to come from, then in order to go and get the radon completely at the opposite end, diagonally of our house, we'd probably have to travel about 50 feet to go and get the radon completely at the other end. That will require a bit of effort to do that. It may require a bigger fan than normal. If we have the opening of the pipe or our pipe more towards the center so that the main draw comes from the center of the floor, it means that in every direction to get the radon in every corner, we only have to travel maybe 20 feet. So it's going to be much easier because shorter distance at that point when we do our draw from the center of the floor. So again, those are the requirements that are in the code, and we're going to see that a little bit more with, I'm going to show you some pictures and stuff of that. The top end permits the connection to depressurization equipment. So like I said, if we have to down the road, maybe a year or two down the road, we measure for radon. We have high radon levels and we need to install a fan. And that pipe that's sticking up a foot above the concrete floor, we simply cut off the pipe, the cap, and we take off from there. We don't actually have to make a hole through the concrete slab at that point. Now that becomes important, especially in areas where you have radiant floor heating, with water pipes running inside your concrete floor slab. If we have to make a hole, it gets very touchy. So make sure that we can make a hole without hitting one of those pipes. So if we already have a pipe there, then it's a big advantage. And again, need to label that pipe that is to be used for radon only. To allow effective depressurization of the space between the air barrier, which is the vapor barrier underneath the concrete floor slab, and the ground, which is the natural ground, the extraction opening, so the end of the pipe, should not be blocked and should be arranged such that air can be extracted from the entire space between the air barrier and the ground. So in all that crushed stone area, that's where we want to draw air from, draw the radon from. This will ensure that the extraction system can maintain negative pressure. And remember what I said about negative pressure, using that term, is we're comparing the pressure from two zones. And the zone with lower pressure is what we call a negative pressure zone. So in this case, we want the pressure underneath the concrete floor slab to be less than what it is in the basement. That will, the pressure in the basement will prevent the radon from coming in at that point. If we have a crawl space, then we still have to do the same thing. We got to put that, air barrier, vapor barrier over the ground. And again, we want to try to at least have a negative pressure underneath that barrier. If we have, sometimes in certain cases, homes with load-bearing walls that cross the center of the basement from one end to the other, that's what supports your main beam a lot of times, or your floor joists. Underneath that bearing wall, you have a footing. So sometimes we create a suction on one side, but once we get to the footing, it actually creates like a dam. It prevents our suction from carrying over to the other side of the load bearing wall. So in case like that, we need to make provisions to have like two suction points, or make so that we can create a suction on both sides of that wall, or find a way that we can create a suction on both sides and not have that footing from that bearing wall blocking us at that point. So again, here, that air barrier system, what we want to do is we want to minimize the amount of radon or soil gases getting into the building. So it's got to be very well sealed. That's what we're getting at here. Now, there's not any type of material that can be used for that. Here, they're giving you an example that the material used as a barrier must conform to the standard, the Canadian standard CGSB 51.34M. And that essentially refers to the typical 6 mil vapor barrier that we see on the walls, or that we install on the walls over the insulation. So that's typically what it's referring to. Again, where the floor on ground is a concrete slab, the air barrier shall be installed below the slab. We don't install that plastic on top of the slab. It's got to be underneath. The joints, because you're going to have joints for sure, they must be overlapped at least 300 millimeters or 1 foot and sealed. You just don't overlap them and leave them like that. So you got to be sealed. Where installed in conjunction with a framed floor on ground or above a floor on ground, the air barrier shall be installed in accordance with Article 925.33, and a floor on ground shall be sealed around its perimeter to the inner surfaces of adjacent walls using flexible sealant. So kind of what they're referring to here is that the vapor barrier that you have over the top of the crushed stone has to essentially come up the wall, your foundation wall, and it's got to be sealed to the concrete of your foundation wall. Now we're going to see different scenarios relating to that, but again, essentially that's what they're referring to. It's got to be sealed. We know that one of the primary points for the radon to get into your home is that cold joint or that crack that forms between the foundation wall and the edge of your concrete floor because of the shrinkage of the concrete slab. So if somehow we could block from underneath that crack, then at that point we'll prevent the radon from getting into the home. So we're going to see different options we can use for that. So these are actual drawings that we see in the National Building Code. And essentially here we talk about an air barrier system. So it's that plastic that's underneath your concrete floor slab. And again, it includes crawl spaces. If you have a crawl space, you have to put that in the crawl space also. And the goal of that is to try to prevent the radon from coming into the basement. If you have a sump pump pit, it must have a sealed cover on it. Otherwise, your pit will simply be a big hole in the floor, and it'll be a highway for the radon to get into the basement. So it has to have a sealed cover. All buildings shall be provided with a rough-in for a radon extraction system. So that's that little pipe that comes up through the concrete floor. So every new house has to have that. Now, active soil depressurization using performance-based criteria, or another option using prescriptive criteria. I'll give you two options. Now, prescriptive criteria is the easy one. That's the one that they tell you directly in the code what to use. And here they're going to refer to crushed stone underneath at least 4 inches thick, a layer of crushed stone underneath the concrete floor slab. That's a prescriptive criteria. Now, if you're in way up north and access to crushed stone is, they just don't have access to it, there's other products that we could use, like there's special styrofoam panels that have grooves underneath the styrofoam panels, etc., etc., that will act the same way. You can create an air movement underneath the panels, just like you're doing through the crushed stone. So those are called performance-based criteria, and they're used in areas where crushed stone is not readily available at that point. Vent risers should be able to maintain negative pressure under the entire floor. Again, if it's separated by a footing, like a bearing wall, we have to make sure that we can create a negative pressure on the other side of that bearing wall also. Prescriptive requirement, it's 100 millimeter thick granular layer of clean coarse aggregate, which is essentially crushed stone. So 4-inch thick layer of crushed stone, that's the prescriptive criteria. And a vent riser shall be capped above the slab or membrane. So again, it's you got to cap it. If you don't cap it, then there's a lot of radon coming in from that pipe. Here, they give us essentially 3 drawings of what they're looking for. So the first drawing, they say just take a small length of pipe, sit it on top of the crushed stone at the center of the floor. So in the center of the basement, okay? Put this small section of pipe, leave it, make sure it sticks up maybe 12 inches. Put a cap on it, make sure it's sitting on the crushed stone, and wherever you go through that vapor barrier or that air barrier, make sure that you seal around the pipe and the vapor barrier, so that there's no radon that could come up around your pipe here. Now, why you near the center of the floor, like I was explaining, in terms of distance from the center of the basement to get to every corner, it's a fairly short distance. That's why they want you to install that pipe near the center of the floor. Make sure you label it, like radon on it, so that somebody doesn't use it to install a toilet down the road. It's got to be a permanently sealed cap, not duct tape or tuck tape or anything like that. It's got to be sealed to the membrane. It's got to be labeled every 1.8 meters or every change of direction. Now, this type of a setup, it's in the building code as an option. I could tell you it's rarely used, because typically what happens as they're pouring the concrete floor, a lot of times one of the guys is going to give it a good kick and it's going to end up in the corner of the basement. So it doesn't stay in place. And if it does stay in place, a lot of times by the time they finish pouring their concrete floor, it's all crooked. So it's not a technique. It is a technique that they give as an option, but it's not a technique that's used very often. And who the heck wants to see this white pipe sticking out in the middle of your basement floor, in the basement there? So it's a technique that's not used very often. So we'll look at the other technique that they recommend. So this one here, essentially it's the same thing, but essentially what you have is you have a T that's in the layer of crushed stone. A little bit more solid, but again, the big question, who the heck wants to see this pipe sticking out of the floor in the middle of your basement? So again, yes, it is a little bit more solid compared to the other pipe. But again, a lot of times once they finish pouring the concrete slab, it's all crooked. So sometimes so crooked that it's not usable. And again, who the heck wants to see that pipe sticking out of the floor in the middle of the basement? So again, it's a technique that's not used very often. The last option is they say, put your pipe that's sticking out of the floor close to the foundation wall somewhere and run a pipe so that the end of the pipe is close to the middle of the floor. So this is the option that most contractors will use. The big problem that we see nowadays is because everybody gets this drawing, you know, makes a copy of it out of National Building Code, and they go to the site and they do their installation. So if you look at the end of the pipe here, you got this little rectangular here that's at the end of the pipe, and we have the same rectangle here, you know, at the top of the pipe. So we know that this is a cap. So most plumbers, most contractors that are installing this pipe, what are they going to do? They're going to install a cap on the end of the pipe here. Now, when we come along and we cut off this cap here to install our fan and our piping to create a depressurization, it doesn't work because somebody put a cap on the end of the pipe. So we asked the plumbers, why did you put a cap on the end of the pipe? Because we want our main draw to come from the center of the floor. The purpose here is to have essentially an open pipe here near the center of the floor, and then we will draw all the radon from the center of the floor from every corner at that point. But they said, well, what we did is we installed perforated pipe here, because in the National Building Code, they don't specify which kind of pipe this is. It could be a solid pipe like we see here, as long as the end is open so that we can draw air from it. So they install, you know, perforated pipe, but they use what's called the B&Q pipe or the SDR 35 pipe, which essentially has two series of holes. They don't have holes all the way around the pipe. They just have two series of holes. And a lot of times when we backfill that kind of pipe with the crushed stone, the crushed stone will come and partially block those small holes. First of all, there's not a sufficient amount of holes, and we put the crushed stone over, we kind of partially block a lot of those holes. So if there's a cap on the end of it, then we can't use that pipe. And a lot of owners get mad at us because they say, well, you know, I paid you know, $1,200 for that pipe to get the contractor to put it in, and now you're telling me I can't use it. Well, it was not done properly. So again, we can't use it. I can't create negative pressure underneath the concrete floor slab because all the holes are blocked in the perforated pipe and there's a cap on the end of it. So that's one of the big things that we're seeing nowadays. That when we say mistakes to, you know, not to avoid, that's one of the mistakes there. Again, where do we put this section of pipe? Where do we come up to the floor? Again, we have to always think of the next phase. Maybe we might have to install a fan in this home to remove the radon, to create that negative pressure underneath the concrete floor. So we got to be able to have it in a location that we could use. Now, I've seen places where they brought up this pipe underneath a electrical panel. Now, how the heck are we going to go and install a fan there when it's underneath the electrical panel? I've seen a place where they put it behind the furnace, and the spacing behind the furnace and the foundation wall was about 10 inches. I couldn't even get to it to touch it. So I definitely couldn't use it. So again, where you put that stub becomes very, very important also. Some people put it underneath, the main stairs of the basement. And if the main stairs of the basement are in the center of the basement, then at that point, where am I going to run my pipe to get it outside? I have to run through the finished rooms, bedrooms and whatnot in the basement to get to the outside. We can do what we call a sidewall discharge, is we can discharge it to the foundation wall, but outside we have to make sure that it's safe where we're going to, throw that radon, because it's going to be concentrated, that radon. So if there's a child's sandbox just on the outside of the foundation wall here, and I'm throwing my radon, which is fairly concentrated, to that child that's in the sand, that sandbox, he's getting quite a whiff of very concentrated radon every time he's playing in there. Same thing if we have a porch, and that's where the people will have their coffee on a Saturday morning when it's nice and sunny during the summertime, and we're blowing concentrated radon in their face. So again, we have to give some thought where we put that so that it's safe to shoot it outside at that location. So that, again, it's a very important decision for the builder. Where do we send that? Another option is we have this, but we could also use a foundation drain, which is the corrugated black pipe that we put on the outside of our foundation. We can actually do a loop inside, on the inside perimeter of our basement, which will pretty well act the same as this pipe here. So we could do that and just put a T and then come up through here. So that's an option that you could look at also. Again, here, what is on the end of the pipe? Almost all plumbers think it's a cap, so they put a cap. Doesn't work. 6, 7 times out of 10, when we come to activate a system because the radon levels are high in the home, it doesn't work because of that. So here are examples of what the plumbers are doing. So they're installing perforated pipe, putting a cap on the end of it. So these are mistakes that we want to avoid. What that actual design is on that, if I go back here, what this is actually supposed to be a rodent screen, like we see here. It's supposed to be free. And that screen is simply to prevent the crushed stone from falling into the pipe. That's what's supposed to be on the end of the pipe. We don't want a situation like we see on the left here where the crushed stone is, the pipe is filled with crushed stone at that point. So here, an example, I did an inspection on one home and I actually had, pardon? Was there a question, Ramelia? No? Okay. So this is an inspection I did on one home where I actually cut off the cap and I put in a rodent screen, which is what's supposed to be. We like to use, instead of using the SDR 35 or the B&Q pipe, I prefer to use the simple foundation drain like we see here. But again, we have a screen on the end of the pipe to prevent the crushed stone from falling inside the pipe. Again, here in the codes, we don't actually see what kind of pipe it is. It could be a solid pipe, as long as the end of the pipe is not a cap. It's a rodent screen. So here again, we talk about best practices. So when we're installing that pipe to the center of the floor, we want to make sure that we have a downward slope. Why do we suggest the downward slope? Is that the day may come where we may have to put a fan, a radon fan, to get rid of, to create that suction underneath the concrete floor, because radon is getting in and the levels in the home are high. Whenever we install a radon fan and go and get the radon underneath your concrete floor, we also get all the humidity that comes from the soil. And on a typical day, we're taking out the equivalent of 1 gallon to 2 gallons of water a day in terms of humidity. So there's a lot of water that runs back here to the soil from our system. And if you have a proper slope going to the center, then if you had a solid pipe here, then that water would drain out at the end of the pipe. If you have a cap on it, then it simply fills the pipe with water. If you had to pass underneath, let's say a sanitary drain or a regular house drain at that point, and we have a counter slope in the wrong direction, then at that point, what you end up is something like this we see on the left at the bottom, is your pipe will fill up with water. And once it's full of water, then your system is going to try to actually draw air through that water. There's going to be blockage, and you're going to hear glug 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 all day long, yeah, all night, because of all that water that's accumulated on there. So remember, when we install a fan on there, just how much condensation and we're going to get in the pipes. Before that, doesn't matter. Doesn't matter if it's full of water. But the day that you put a fan on it, because you need to reduce the radon levels in the home, that's where you start having problems. So again, here, different things we see, and here with that famous B&Q pipe or SDR35, you see that there's only 2 series of holes. And if the plumber was to put those 2 series of holes pointing upwards, then we get something like this here. We get the pipe filling up with water. So if you're installing that kind of pipe, we suggest that you have one of the series of holes pointing downwards. So if you get condensation inside the pipe, then it's going to drain out into the crushed stone layer. So there's different types of, where you're going to have that radon stub, different ways of doing it. They have special saddles that you can buy for a drain tile or the foundation drain. It sits on top, and then you simply have to cut out a hole and put in your pipe. If you want to increase your draw at the end, where you could put a T and with some extra lengths of foundation drain pipe at that point. But here you see those two series of pipes. Again, like I was saying, if this is the pipe that you want to use, just make sure that close to the elbow, where your radon stub is, that elbow that's right underneath, put one of the series of holes pointing downwards, or drill a couple of holes in the bottom of the pipe so that the water, the condensate that's coming back, is going to have a place to drain at that point. So here's examples where you could see the radon stubs coming through the floor, and they're all labeled radon, radon, radon. Those are good practices. Glued caps. That's the best practice. This is the stuff that you want to avoid, where you have no cap at all, a little orange cap, a test cap. Some of them, they just tape it with tuck tape. Some they fill with cement. This one has like what we would find in the floor drain. Doesn't seal. So any situation like this here, for sure, the radon is going to get into your home. It's going to be a highway for the radon to get into your home at that point. When we backfill around the smooth wall SDR35 or B&Q pipe, what actually happens is what we see here. There's not a lot of holes. You remember, there's 2 series of holes. And when we backfill with the crushed stone, what happens is that crushed stone comes and partially blocks the holes that are in the pipe, as you can see here. So when we come to use it, even though we have the holes there, a lot of times we're not able to draw a lot of air through those holes because they're partially blocked with the crushed stone, like we see here. So like I was saying, 7 times out of 10, it doesn't work for us. We have to make our own hole and abandon the pipe at that point. So here's actually a view from inside that pipe, SDR35. You can see here to the right, the actual end of a crushed stone is actually blocking the hole almost 90%, and the other side maybe 70%. So if we only have on a length of 10 feet, we only have maybe 40 holes or 50 holes, and the 3/4 that are blocked like this here, and the plumber on top of that put a cap on the end of it, then forget it. We can't draw enough air underneath the concrete floor slab to create that lower pressure there. If you're using, like we use a lot, the foundation drain with no filter on top there, At that point, you could see that the crushed stone doesn't come and block those holes that are in the, it kind of sits on the mountains, and the holes are all in the valleys. So less chance of all those holes being blocked at that point. So we found using the foundation drains to be the better option for us a lot of times. Now, if you want to increase the areas where you're going to be drawing air from at the end of your pipe, you can put a T on the end of your pipe, which will create on the left here two openings where you can draw air. This one will put 2 T's, so you have 3 openings where you can draw air, and again here 2 openings. So if you want more opening at the end of your pipe, you can do stuff like that. There's even cages that you could put on the end, metal cages that create like a plenum at that point that you can actually install also. So again, here with the saddles that we see, you see on the top left here, essentially we just cut out on top of the perforated pipe, and that's where we take off from. So it's actually sitting on the saddle, which is sitting on top of the pipe, and always with wire mesh at the end of the pipe, just to prevent the crushed stone from falling into the pipe. Here are some more examples. Now, a lot of times when we get called in, the plumber has passed before us. So he's installed all of his pipe, and now we got to get our pipe to the end of our pipe to the middle of the floor. So we have to, a lot of times, we're struggling to work around their pipes. If we get there first and they know it's for radon, sometimes they'll cut our pipe so that they pass their pipe. So sometimes we're better off to come in after. But in certain cases, we may have to go under their pipes. We may have to go around their pipes. If you're using the white SDR35 or the BNQ pipe, it's hard to get around obstacles like that. So again, this is where perforated pipe helps us a bit to get around. Wherever any pipes, columns, posts penetrate through that vapor barrier, that air barrier, you need to seal around that pipe. Like here, you can see there's a lot of big tears around the pipe there. The pipe's going through it. You can see they just took a knife and just cut through the membrane around the pipes. Now, if you don't seal that properly, a lot of radon is coming in around those pipes here. So we have to take the necessary steps to seal around that. So you can see here, this was a membrane that we installed. So you can see that wherever the pipes came through, it's sealed. And wherever they overlapped, we made sure that we have a bead of acoustic caulking. We need to overlap by 12 inches. So we have a bead of caulking there that where it overlaps, and we put tape. Now the tape, a lot of times, is just to allow the caulking to dry. As we're walking around on it, we don't want to trip on the end of and we want to make sure that the sheets don't move on us and breaks the seal. So that's why we'll put tape also at that point. Underneath the bathtubs, this is typically what we're seeing. You'll see on the left here, crushed stone, nice big hole underneath the bathtub. In the new construction, they put a box, nice big hole. Underneath the shower here, you can see the crushed stone, nice big hole. These are big holes. These are probably about 16 by 16 holes. So typically that's just left there. After the plumber is finished installing his P-trap, that's just left like that. So again, there's a lot of radon coming through that home. Remember, it's being sucked in with this stack effect. So if you have a sump pump, a pit, same thing. You need a sealed cover on that. Otherwise, it's a highway for the radon to get into your home. A lot of times, a simple fix would be just using expanding foam. We could fill that hole pretty quickly. We do that a lot of times. We can, to seal up against the foundation wall, we mentioned that you should be looking at bringing up your vapor barrier up against the wall and sealing it on the wall. Another option is to seal it on the footing. So again, the weight here, the weight of the slab on top of the plastic here is going to squish that bead of acoustic caulking, and it's going to make sure it's sealed at that point. So that's another option you can use, sealing on top of the footing. And in certain cases, if you have an ICF home with styrofoam forms, that may be your only option. There's not too many products actually stick to the foam itself. Most caulkings will eat it away. So here, like we were saying, the option coming up with your plastic, your vapor barrier, and actually sealing it up against a wall. So even though you get a good gap forming between the foundation wall and the edge of your concrete slab, the radon can't get into your room here, into the basement, because it's sealed. Your vapor barrier is sealed up against the wall. So that's what you want to do, is you want to make sure that the radon can come in. We know that this is going to happen. The shrinkage is going to occur. And in a lot of cases, that shrinkage is going to continue for a period of maybe 3 to 4 years. So you may have just a hairline crack the first year. And if you look at the same crack 3 or 4 years down the road, it may land at an 1/8 of an inch. So again, it's shrinkage, just slow shrinkage over time. So this is actually technical specs that are provided to a lot of plumbers and builders from the APCHQ in Quebec. Now let's look at the details here. What are their weak points? So here, essentially what they're giving you as information, you have styrofoam panels on the wall that comes and sits on top of the footing. You have styrofoam panels on top of your crushed stone, and then you put your vapor barriers over on top of the panels here, and you make sure that it's well sealed where they overlap at the joint at the bottom here. Now, what actually happens in a case like that is your radon is going to bypass and come up through the back of the styrofoam panel on the wall, because what happens is your foundation wall is never really smooth. It's rough. So when you put your styrofoam panels on a wall, there will always be a small gap behind the styrofoam panels. And at that point, that's where the radon is going to be coming into your home, is behind or between the styrofoam panel and the foundation wall at that point. So how do we prevent that? Here are some options here. So if that was the case, you could actually take a small strip of 20-inch wide vapor barrier. You glue it to the wall. You install your styrofoam panel on the wall, and you can actually take the end and come and tack it temporarily to the surface of the styrofoam panel here. You install your styrofoam panels on the floor. You're going to have a vapor barrier on top of that, a vapor barrier coming down the wall, and you could seal all 3 joints at that point right here. So then you got an actual seal behind or between the styrofoam panels and the concrete wall that will prevent the radon from coming through. Another option might be to actually seal it on top of the footing. That's another option there too. So again, you can see here, they actually have a bead of acoustic caulking behind on the wall behind the panels. And that's actually what they did. They just tacked it temporarily on the wall. They did their styrofoam on the floor, vapor barrier on the floor, and then they kind of overlap all the different vapor barriers at that point. When we have a load-bearing wall with a footing, we got to make provisions so that we can create a suction on both sides of that footing. So here, to give an example, we could run a pipe through the footing itself so that we can actually have suction from both sides at that point. So something that you could look at doing. But remember that if we create a suction only on one side, the other side, the radon could be coming in to the basement from the other side where you don't have a suction. We mentioned also about using performance criteria. So if you're way up north, you don't have access to crushed stone, then these are examples here of stuff you can use. Geotextile matting, which will create essentially kind of a pipe that you can have underneath the slab. You create a suction on those. So you interlink them all, something like a ladder there, the rungs of a ladder. This one is styrofoam panels, and you could see that underneath the panels, it's sitting above the gravel, so you're able to create suction. You have ventilation channels underneath. that you can create suction at that point. So those are available in areas where you may not have crushed stone. Up until now, we've been talking about the requirements of the National Building Code or the building codes. So essentially, you have to have the crushed stone, the vapor barrier, the piping in the crushed stone underneath the concrete floor slab, and we have to come up through the floor with a small section of pipe and cap it off. So up until now, that's what's in the codes. Now, right now, because I'm sitting on the task groups with the National Building Code, and we're looking at what's coming up for the 2025 National Building Code version. It's looking good for the obligation of a passive vent, because with a passive vent, you will get some reduction in radon in your home. With what's in the code now, with that pipe that's capped off, you get no reduction at all. You just have it ready kind of deal. So with a passive vent, the way it works is you have a pipe running from that piping that's underneath the concrete floor slab, runs throughout the house and comes out by the roof. So the heat that's around your pipe is actually creating a chimney effect inside your pipe. So it's actually going to be drawing radon continuously while you're in your heating seat and throwing the radon outside. So that's just a pipe, no fan. So again, that's what we call a passive vent, is you got to run it from the underneath the concrete floor slab all the way up to the roof, as straight as possible. Anytime you have elbows, it reduces your chimney effect inside the pipe. So essentially, this is how it works. You have heat around the pipe, and essentially it's creating a stack effect inside the pipe like a regular chimney. And at one point, it's going to draw the air from underneath the slab and exhaust it outside. When we're doing that kind of work, one of the things that I like doing is kind of overlapping the plans one on top of the other. And what I'm looking for here, I'm trying to find walls that are essentially one on top of the other, from the basement all the way up to the second floor. So I'll overlap the plans and I'll look for walls that I could find that would be one on top of the other. And that's essentially where I'm going to be running my pipe from that location. Again, here it's a task that I do, and I'm always able to find a wall somewhere that I can use to run my pipe as straight as possible to the roof. And here's the trick: as straight as possible to the roof. If you have a lot of 90-degree elbows, then you're losing your chimney effect inside your house at that point, inside the pipe. So here's an example of one I did for a client where I overlapped all the plans, and I found a location where it runs up, through a wall. You talk to the builder and you say, okay, this is the wall where I need to run up. So you need to make that wall a 2x6 wall. The pipe I'm running up is 4-inch. So it doesn't fit inside a 2x4 wall. So, I work with the builder and say, okay, that wall, you need to make it a 2x6 wall. This wall on the second floor, you need to make that a 2x6 wall, or at least screw or nail a 2x2 on top of the 2x4 wall. So we'll work with the contractors to make suggestions so that we can get our pipe all the way up to the roof outside with minimum disturbance inside at that point. 3-inch pipe versus 4-inch. If you allow it up to the choice to the builder, he'll always choose 3-inch. Now, 3-inch will probably work for about 75% of the time. But as soon as we have a lot of volume, or if you have to put a fan on because you need more suction underneath the concrete floor, the 3-inch pipe in certain cases may not work. It'll create too much restriction for you. 4-inch will always work. So go up with 4-inch all the way up to the roof. So here's some examples of what we would see as a passive vent. Now, whenever you have a passive vent, make sure you label it. Lots of labels, especially if you're using ABS pipe, black ACS pipe, because you never know, in 5-10 years, maybe the new homeowners are doing renovation, they're installing a new bathroom, changing the location of their bathroom, and the plumber's looking for a pipe where he could tie on his toilet, opens up the wall, and guess what he sees? A nice 4-inch pipe inside the wall, Blackie. He's a happy camper. Oh boy, my job is going to be easy today. I've got a nice 4-inch pipe here, black pipe ABS that I can tie my toilet into. Well, I could tell you what we're going to see underneath the concrete floor and that crushed stone is not going to be making him a happy camper in a month or two. So again, the trick here, passive vent as straight as possible. And we recommend using only 22.5-degree elbows for the offsets. So if you have to go from one wall on the first floor and you have to offset maybe a foot to go to underneath the wall or through a wall on the second floor, as much as possible, 22.5 degrees. That's the ideal. Types of pipes we can use. We can use the black ABS pipe, which is called Schedule 40. And when we say Schedule 40, essentially what we're looking for is a pipe, 4-inch pipe that has at least a 1/4-inch wall thickness. So the ABS pipe does. You can use white PVC pipe, 633 is what they would normally use for a gas furnace, as an example. Gray PVC pipe, system 15, they would use that for commercial plumbing in small commercial buildings. The gray PVC pipe XFR, they would use that for commercial plumbing in high-rise buildings, as an example, or schools or something like that. Gray PVC pipe, IPEX Radon X, which is actually a special pipe that's made by IPEX. And the advantage of that pipe is that it's marked, all the full length of the pipe, it's marked radon, 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 radon. So if a plumber has to hook in a toilet, he'll see that it's marked radon everywhere on the pipe. So at that point, he probably wouldn't tie in his pipe into that one there, or his toilet into that one. You have Zertec pipe, other PVC piping, which considers Schedule 40, like the aqueduct piping and stuff like that you will see in the street. And no longer can you use the tin wall pipe or the PVC SDR35 or the BNQ pipe. That's no longer accepted. The reason for that is that during the summertime, the air that's going to be running through your pipe, which is coming from underneath the house, it's going to be fairly cool. And you're going to get condensation on the outside of your pipe, especially if you don't have air conditioning in the home. So that condensation on the outside of the pipe, especially if you're passing inside the walls, you can get mold buildup inside the walls. So again, you would not necessarily see that with thick wall pipe, Schedule 40, but with the tin wall pipe, because the walls are so thin, you'll get condensation on the outside of the pipe. And the manufacturer only guarantees it and only recommends it for underground. So again, we can't use that above the floor, in other words. We recommend using a color other than ABS, or using pipe other than ABS. And again, for the simple reason that, down the road, if the plumber comes to put in a toilet, he'll think twice before cutting into a white pipe or a gray pipe there. If you're using black pipe, lots of labels, lots of labels. Don't be shy with your labels. Radon, radon everywhere, so that the plumbers don't tie into it. Anywhere that you're going through a cold space, like an attic as an example, unconditioned space, you need to insulate the pipe, at least to a factor of R8. So about 2 inches thick of insulation. And it's got to be covered with a vapor barrier. Again, for the very reason that if your pipe is cool, you might get condensation on the outside of the pipe in the summertime. Here's an example of one job we did recently, just before Christmas, where there was no insulation on the pipe in the attic. And we had to cut the pipe, and you could see how much ice buildup was inside the pipe. So landed in the attic, you want to minimize any horizontal runs. And the pipe in the attic should be insulated. So here's an example of what not to do. You have long runs of horizontal pipe. And even if I wanted to install a fan in the attic here, I couldn't, because the fans have to be installed vertically to allow the condensation to return through the fan back to the source, which is the ground. If I was to install a fan horizontally, then water would accumulate in the belly of the fan, which is made like round, And at that point, your squirrel cage would be running in water and would burn your motor pretty quickly. So again, this is stuff that we see often, and that's why we can't activate that system, because it doesn't have the proper slopes. Can't install our fan in the attic. Avoid horizontal pipe runs whenever possible. Again, the trick here, as straight as possible up to the roof. Vertical pipes must be supported every 8 feet. And again, what we see a lot of contractors is they don't necessarily have a support. As soon as we put a fan on it, there's a small vibration that occurs. And if your pipe is not well supported, then you hear echoed noise throughout the house. And they're wondering what's causing that noise. And they point the finger at you. You installed that fan, you created that noise. But it's because the contractor that installed the pipe didn't support it properly. Use as much as possible only 22.5-degree elbows for offsets rather than a 45 or 90. Always have a counter slope to allow the condensation that's going to occur in the pipe to return to the source, which is the crushed stone layer at that point. So here you can see an example of how much condensation that we see in our pipes. So there's a lot of water going to be running back in our pipes. We did that same job where we had that pipe that was not insulated in the attic. Well, in the basement, the plumber who installed the piping didn't have the proper counter slope to allow the condensation to run back to the source. In this case here, we removed about the equivalent of a 5-gallon pail of water that was just sitting in the pipe because it could not drain back to the source. So again, the plumber had to come back and redo his work there. Where we're going through the roof, maximum maybe 12 to 16 inch max. And here's a picture of a pipe we took last winter in January, just after a real cold snap of -30. This is what we would see on the roof. Here's an example of the efficiency in terms of radon reduction for a passive vent. And here, passive vent, remember, it's simply a pipe going all the way up to the roof from the concrete floor. So here we actually did the piping and we installed a valve at the bottom of the pipe, where close to the concrete floor. So for 1 month, we closed, or in this case here, for 1 month, we left the valve open. So this is the reduction we were getting. So your pipe was actually working. The next month, we closed the valve. So it's as if you did not have a pipe anymore. So we could see the radon levels increase dramatically in the home. And we could see places there, it went up to almost 2,000 in this home here. A month later, we opened the valve again, and you could see how much would drop. So the passive vent in this case was very efficient at keep maintaining good levels of radon in the home. So we were able to get reductions between 50 to 80% just with a pipe, no motor, just with a pipe. Here's another example here of another home in our project. Again, the first month the valve was open. We closed the valve. So this is the month, and you can see here again, the levels were in the thousands there. Remembering that the actionable level set by Health Canada, it's 200. So here they were running way above 200. And then we opened the valve again, and you can see how much of a reduction we were getting just with that pipe. Here's another example again, where we had it open, and then we closed it here, and you can see the radon levels increase. Closed, and then open here, and it goes back down. So the passive vents do work. They may not correct your problem 100% if your levels are really, really high. But you could see here that, you know, you're in the close to thousands here, and we were able to reduce it below 200 just with the pipe. No fan. Active systems. Well, when we talk about an active system, essentially in that passive vent, we're simply cutting the pipe and putting in a fan. So here's an attic installation. So we cut the pipe, put in the fan. Passive system, it's only the pipe, no radon fan, no electricity. So when we compare an active system versus a passive system, fan powered option with a fan, we can get somewhere between 90 to 99% radon reduction. A more flexible pipe route, we don't care if there's elbows, 90-degree elbows in the piping system. Our fan is going to create a sufficient vacuum to draw the radon from underneath the concrete floor slab. Passive system, we can get about, on average, probably about a 50% reduction. So if your levels are above 400, maybe you might have to go with install a fan. But if you're between 200 and 400, maybe that passive option would fix the problem for you. Now here, in terms of pipe routes, we got to make sure that we minimize any 90-degree elbows. So you're using only 22.5 if possible. Once it's installed though, it's easy to slip in a fan in the attic. We just cut the pipe, and at that point we install a fan. For sure, the fan powered options are always more effective at reducing the radon levels than a passive system. And typically, if we follow all the instructions, we're using the smallest fan that we have on a truck, compared to a home where you may have compacted sand or clay or compacted gravel underneath the concrete floor slab. The benefits, for sure, with a fan powered option, we're going to get the maximum radon reduction. With the passive system, for sure, we're going to get some reduction, and we don't really have any operating costs. We're not running a fan here. Greatest flexibility, we don't care if there's elbows, horizontal runs with a fan, we're going to make it run. We're going to make it work. Not the case for a passive system. If we have a lot of elbows, horizontal runs, we may have to go with a radon fan at that point. What do mitigators like me say about activating that kind of a system that was put in by a builder? So essentially, common comment, the pipe in the attic that exits the roof is so low that there's no room for a fan. Like we've seen in one of the pictures, there was no room for me to put in a fan vertically in the attic. No power in the attic. The passive system, the pressurization system, is tied into the attic vent pipe, the attic plumbing vent pipe. So rather than have two pipes go to the roof, some builders will stick it into the plumbing pipe. Pipe that is sloped the wrong direction, and again, we've seen a picture of what we're referring to here. I took 5 gallons of water out of the pipe. I was just stagnating there. Improperly supported pipes, which could cause vibration inside the walls that will echo throughout the house. Pipe that squeeze into the wall that will vibrate drywall, that's what we're referring to. ABS pipe whistles, I don't really agree with that, but some mitigators say that. Suction pipes that are embedded in footer or soil. In certain cases, the builder knows that there's going to be an inspector coming in checking for that pipe for the radon. So they dig a hole in the basement, they drive down the pipe 2 feet into the ground where the crushed stone is, and they leave it stick up above the soil, above the floor. So not the plumber, but the inspector comes around, he's looking for that radon pipe. He sees a pipe coming out of the concrete floor, it's marked radon on it, checks it off, done. But in reality, when we come to activate it, we're trying to suck on that dirt, 2 feet of dirt there underneath the crushed stone. So things like that happen. Piping configurations that do not treat every slab. So we may have a bearing wall where we're only treating one side of the bearing wall, and that footing is preventing us from getting a suction on the other side. So again, we see stuff like that. We've even seen some of the piping used glued with silicone or ABS glue used on PVC pipe. So again, whenever we're activating something like that, we make sure that we don't offer any guarantees on the pipe because we did not install it. Some of the comments, liability. If I touch it, then I own it, and I become responsible for it. So again, there's a problem because there's a leak in the wall. Who's the owner going to point the finger at? It's your fault. You're the last one to work on it, so it's your fault. Never had a problem before that. Temperature is again inside the wall. In the summertime, if you're using a tin wall pipe, you could get condensation on the outside of the pipe, and you get mold buildup, like you see on top of the fan here. Again, typically we say if we install the system, we can offer full warranty, full guarantee, but can't guarantee it if we're using somebody else's pipe. But this is the end of the presentation. You have my coordinates here. So if you have your phone ready or something like that, or a piece of paper, you can take out the information here. If you have questions down the road, you can give me a call. My email